I've done, really hundreds of videos for my other courses, but this is new. I can see that my notes that I've put together will take more than one video to get through, or more than two, probably 3 or 4. So this is kind of interesting to me to see. Well, let's continue on. And the reason it's going to take so long is I'm giving you every possibility that I can think of. So if you get it and you're sure that you've got this material down, you can go on. But if there's any doubt, just keep going. I'll give you lots and lots of problems to work with. But you should, if you have any idea what's going on, you should pause it and try to get the answer before I do. Use this as a check. The rate of reaction with respect to CF4 from 0.4 seconds to 0.5 seconds. Now we have this equation, or that term, and then we know that's going to be the concentration of CF4 final minus CF4 initial over T final minus T initial. And they tell us, I'm going to bring this over, the final time is 0.5 seconds, and we'll add in that significant figure, 0.4 seconds over concentration of CF4 at that time. I'm not going to bring the sheet over. You should have this data, or just trust me that this is what it is. And then minus, big fat minus here, 3.75. And we have that, and where's my calculator? Okay, so we have 3.87 minus 3.75, and then divided by 0.1. So we get 1.20 molars per second. Notice that it's positive. That positive means that it's a product. We're building in where there's more concentration as we go up in time. So this term on the bottom is always positive. For reactants, this number is smaller than this one, so it's negative. So that indicates that you're dealing with a reactant. Number is going to be larger than this one because it's a product we're building in. So this value here, this should always be positive for a product. So that's a check for you to do. If you know that you're dealing with a product and you come up with a rate of reaction that's negative, you've done something wrong. You flip these numbers around, something went wrong. Okay, let's do it for, looks for CF4 from 0.5 seconds to 0.6. So 0.6 seconds. Now we can go even faster. And on top we have for, oh, dang it, I got rid of the 0.6, so let's do something a little different here. Let's go from 0.0 seconds to 0.3 seconds. I've been going up one increment, 0.1 second at a time, just cause. But there's no reason that we can't jump, that we can't use any time frame that we're given. We can start at any point and end at any point. So let's do something that is not just 1 or 0.1 seconds difference. So, and then we have, so it's 0.3 seconds. And I don't make any apologies. I'm going to be doing this a lot. I mean, this was just a mistake because I got rid of that 0.6. I used to have the data, I think it went all the way up to 1 second, but it just took up so much room. But during these problem sets, I may change numbers just because it's beneficial for the students to see something new as well. So even if this was correct, it doesn't give us as much new information as jumping. Students may see that since I always make it one increment, 0.1, that you can't go any further. Of course you can. You can use, if you have, you can go from 0.00 seconds up to 0.5. You can go from the start of that chart all the way to the end, no matter how large the time span is. So 0.3 seconds for CF4 is 3.5 molar, and then 0 seconds is 0 molar. Nice and simple. And this comes up, so this is 3.5 divided by 0.3. So 11.7 molars per second. Positive, you need to have that molars per second, and everything will be fine. Okay, now let's go. I'm going to give you this next set. The one thing I've done here is it's all of these species from 0 seconds to 0.4 seconds. So that's what I'm going, all of them will be that. Methane, fluorine, CF4, and hydrogen will all be from 0 seconds to 0.4 seconds. Here's the data. If you want to freeze it here and try to do that, that's fine. And you know, at this stage, it really is important that you participate. If you're watching this when you're driving or your friends are over and you know the Xbox is going and you can barely hear me, don't do that. You have to focus. Try to do this. It's not enough to watch me do that and say, yeah, I kind of get it. You need to be fully prepared for the exam. The exams are not long, but you don't have a lot of time either. And I'm not going to sit there and let you take 6 hours to try to crank out a problem when you're not sure what you're doing. That's not going to happen in any course from now on. All the way up, you're going to have a very strict time time restriction on all of the exams you take. You have to not only be able to do these problems, but do them very quickly. So let's see. So we have methane. And now I'm just going to do it pretty quick, and I'm going to add in that significant figure. And 4 seconds, or 0.4 for, I'm going to just put this line under here. May not be able to see that, but that's okay. It's really just for me. And then we have 2.25 molar, 0 molar. And so we have 2.25 divided by 0.4. And then we have 5.63 molars per second. And let's see. Oh, I'm sorry. Now, again, I'm not going to apologize for these calculations. There's lots of things going on, and if I make a mistake, I'll correct it. If I don't notice it until after I review the video, I'll delete it and start again. What did I do wrong here? That was a positive value. So it can't be. It has to be a negative value. So I did something wrong in here. You can see that when we start at 0 seconds, there's 6 molar. This had to be a 6. This value has to be greater than this one. And when I'm trying to do everything at once, it gets a little tricky. Happens in class too. And you know, you shouldn't give up on the course or on me because I make this error. These are ones that students normally make, and I'm telling you the correction. I didn't have to wait for the video to see that I made a mistake. I saw that was positive. I knew there was something wrong. Probably would have caught it when I went back to redo the numbers, but I'm going to do it here. But that is fine. It's a negative. I double checked. Everything looks good. Let's do the fluorine. Again, 0.4 seconds, 0.000 seconds. For the fluorine, it is 4.5 molar. It starts out as 12, caught at that time, and now we have 4.5 minus 12 divided by 0.4, and we get minus 18.8, which should be twice as much as the value above. With rounding, it makes sense that that's what it would be. Now, we should, I'll bring those numbers back when we look at this. We have CF4, same time period. So it's 0.4 minus 0.0004. Then we have, or 0.000 seconds, and then we have 0.4 for CF4 is what? 3.75 for the final, initial. And we have 3.75 divided by 0.4. And we come up with plus 9.38 molars per second. Let me make sure we're on screen. And if you notice, that is the positive, same number, but for as we have for methane, except that the sign has changed. For methane is minus 9.38, and it should be, because it's 1-to-1 as far as the coefficients of the reaction. So it's a good thing to keep in mind. And then we have this one here is for methane, or for hydrogen, it's 7.75 molar, 0.00.4 seconds, 7.75 divided by 0.4, and this comes up to be, let's see, I get 19.4. Let me see what, Okay. Now, again, this should have been 18.8 molars per second, because it has to be, because this is 2 to 2 or 1 to 1 for fluorine. Should have the same number, only it should be positive. Well, that's because this is 7.5. Let's see if that matches up now. 7.5 divided by 0.4. 18.8. So I was just looking at the number below on that chart, and on the exam everything would be together. It'd be a little trickier. So again, no apologies here. This is the kind of thing that happens when you're working with this many numbers. You have to double check your things all along, and be prepared. Either if you're in my lecture, same thing's going to happen. Going to be doing these problems out, and in the lecture you're free to tell me that. Ask me the questions about that. So should that be that number? It's going to happen. When I do out a calculation that lasts 20 minutes, very likely to happen, and it's a good way to check on what's going on and follow along with the problem, see if there's any little mistakes like that. Generally, I'll check. I will definitely catch them on the video, or I'll redo the video. But that's another thing to be watchful of. That's a nice check, since you already know what the value should be. The number should be, and it should be the positive of the reactant for fluorine, which was negative 18.8. All right, let's continue on. And we have consider this reaction. How is the rate of reaction? Okay, now we found the actual numbers for each species. When I say species, I mean reactant or product. I don't say molecules, because sometimes they're atoms, sometimes they're ionic compounds, so species covers everybody. So when I say species, I just mean anything that's part of the reactant, or of the reaction. So we found the general form of the rate of reaction, and then we found the numerical values for the rate of reaction with respect to each species, but now we want to relate them. How is the rate of reaction of methane related to the rate of reaction of hydrogen? Well, we can look at it for, let's take the actual example from the last time here. We found for the rate of reaction of methane from 0 to 0.4 seconds was minus, I'm just going to put 9.4 molar per second for methane. For hydrogen, it was plus 18.8 molars per second. That's for hydrogen. So we can see from the data that the methane is 1/2 the rate of hydrogen, and also a negative value. So you don't need to see that. You can actually think of it a little differently here, like I'm about to explain. But you can see the difference, that the rate of reaction for methane is a different number and a different sign than hydrogen. So we want to compare them. So we can see that since it's a reactant, what we want to do is we want to set these two guys equal to each other. The rates of each to each other. That's what the problem is all about. We want to. Well, we can see that these from the numbers that they're not equal. But if we take 1/2 of this side, then we have 9.4. If we make this negative, now they're equal to each other. You might say, well, that just seems like out of the blue, but it's something that we do each time. If we want to, instead of talking about just the rate of reaction of each of these individually, and that's just those terms, they each have the same form if we want to talk about them individually, but if we want to relate them, then what we do is we take the rate of reaction with respect to hydrogen, we take 1 over its coefficient. Its coefficient is 2. We do the same thing on this side, but 1 over 1 is 1. Any reactant, we put a negative, because this value is always going to be negative. For the product, it's always going to be positive. So if we do that, if we take 1 over the coefficient for each of them, we take any reactant and make it negative, then we now set them equal. And if you put that, you look at these numbers and make that negative, that would be 9.4. Take this number and divide by 2, it's 9.4. Now they're equal. So it's how you relate the rate of reaction of two different species. To relate them, we have to make them the same number. And they're going to be different numbers because, well, if one's a reactant, one's a product, they're definitely going to have a different sign. So that's how you do it. You take the 1 over the coefficient in front of your rate of reaction, and for any reactant, we put a negative. So let's take a look at the next one here. How is the rate of reaction of methane related to the rate of reaction of fluorine? Well, the rate of reaction of methane is this. The rate of reaction of fluorine is this. We already knew that. They're not the same though. We take 1 over the coefficient and negative of both sides because they're reactants, and now they're equal. Of course, you say, well, there's 2 negatives. You could certainly get rid of those, but it's a good thing to do kind of mechanically. Just make sure you get everything in there, and then reduce it if you need to. So by doing that, and you can take the numbers that we got. We had negative 9.4 or 9.38, and then negative 18.8, but we make it 9.4, negative 9.4, just so it's easy to see when we round up. And you see this is negative 9.4, this is negative 18.8. Taking the negative of both sides makes them both positive, divide by 2, now they're both 9.4. So we've related them. So it's really fairly easy to do. And even if you don't quite get it, and this is going to happen a lot through this class and through more advanced courses, if you can see how to do the procedure, that's enough for now. Do it. And then maybe you don't quite get what's going on, why we're doing it, but this procedure is very simple. We take 1 over the coefficient in front of the species. If it's a reactant, make it negative. That's it. That's all you have to do. It will come in time. Sometimes when I took physical chemistry, sometimes some of the concepts didn't hit me until the next summer, but I could still do the problem. It was just later on, it's, oh, yeah, that's why we were doing that. But this won't take that long, but sometimes students won't make a move. They won't budge until they absolutely understand exactly why they're doing it. But the procedure is very simple. And if the more you do of these and just attack these problems, you're going to be able to figure out why we're doing it a lot quicker than just giving up on it. So you want to just do this out. 1 over the coefficient for each. They're 1 and 1, so that's it. So, and then their methane is the reactant, so negative, done. Now, what is the rate of reaction? Not with respect to any species. Well, the rate of reaction, and Rxn for reaction, is any of these terms that we have manipulated. And so the rate of reaction is going to be for methane, and that's equal to, let's see, for fluorine, so it's negative 1 over. So that value, that now we've converted all the species into the same value. That value is the rate of reaction, the general rate of reaction. And often that is given as the value, because then once you know that value, so these are now all, I guess they'd all be 9.4 molars per second, and that's the rate of reaction. From that number, you can convert back to any particular species. Because when we give it for one particular species, then we leave out the others. You can see that these are all, each of these that has been changed around, this one happens to be exactly the same, but each of these has been changed around, and that's the rate of reaction, the general rate of reaction with respect to no species, because they're now all, we don't have to worry about any particular species. You could certainly give the rate of reaction of methane and figure out the rest, but generally what's done is you find the general rate of reaction, and that's used if you want to convert to any of the other species. And that's the deal.